Hi, everyone, and welcome to Physical Geography 100 Lecture Podcast Series. I'm your instructor, Brian Krause, and today we're going to begin Chapter 2, which introduces concepts about the study of the Earth and how we're going to reference things that are on the Earth's surface and reference them onto a map. So in this mini lecture, like all mini lectures to come, I'm not going to cover all topics or ideas presented in the text. Rather, my aim is to highlight a few of these key ideas and then discuss them in a bit more detail. So in this lecture podcast, I've also included some non-graded quizzes, kind of concept quizzes at the end of this podcast.
So a map is a fundamental tool of the geographer, and you can quickly tell this by just kind of skimming through your book and take a look at all the maps. The book is a tremendous amount of maps, so it's quite important. And so a map is a two-dimensional representation of the Earth and the spatial distribution of selected phenomena. So with a map, one can illustrate this spatial distribution, example of geographic patterns. For example, where have earthquakes occurred in California for the last 10 years? We can find those locations. Where is there drought? Where are volcanoes? All these types of things are spatial distribution of some kind of geographic pattern. And almost any kind of phenomena can be mapped. And maps provide this wealth of information. And the information collected to create a map is called spatial data. And I just kind of mentioned spatial data of, for example, of where earthquakes occurred in the last 10 years. And this is spatial data. And the reason why it's spatial data is because where these earthquakes occurred have some geographic location on the Earth's surface of where they occurred, or below the Earth's surface of where they occurred. They have some latitude and longitude. And so any kind of thing that has a latitude and longitude that you can put on a map, for example, your house, a fire hydrant, a tree, a road, a river, mountains, all these things have some kind of geographic location. They have a latitude and longitude, so they can therefore be mapped, and they are collectively referred to as some kind of spatial data. So maps can depict two kinds of data. Qualitative data, and is classified or shown by category rather than amount or rank. So for example, if I were to make a map showing different types of soil, loamy soil, clay soil, and so forth, I could make a map showing these different types of soil, but I'm not going to be saying anything about them in terms of if one's better than the other, if there's more of one than the other, or so forth. I'm just going to say this is where this type of soil is, and that's all I'm going to say. Same thing can be said for animal species, for example. I can make a map showing animal species in southwest Idaho and where their habitat is. I'm not going to say if one species is better than the other. I'm not going to say there's a certain amount of this species. I'm just going to say this is where this species' habitat is. So that would be an example of qualitative data. The other is quantitative data, and it's expressed as some kind of numerical value, like elevation in feet or meters, or temperature in degrees Fahrenheit. So these would be some kind of ranking where you can maybe say there's X amount of species, or in California there has been X amount of earthquakes that have occurred since 2010, for example. So there's some kind of numerical value associated with that data. And there are many different kinds of maps that serve quite different purposes. And we're going to look at the following types. We're going to look at reference maps and thematic maps. So a reference map, or a navigational map, are created to help you navigate over the surface of the Earth. And these kinds of maps show where particular places are located and can be used to navigate your way to them. For example, street maps such as Google Map, or your common highway map that you would have in the glove compartment paper map that you can kind of show how to get from point A to point B, and so forth. Those are kind of your reference maps, and those are the types that you're probably most familiar with and use on a more regular basis. Now you know we have GPS navigation in our cars, and that's another example of a reference map. The other type are thematic maps, and are used to communicate geographic concepts like the distribution of densities, spatial relationships, magnitudes of something, movements, and so forth. World climate or soil maps are notable examples of thematic maps. And there are four common techniques for depicting geographic data on a thematic map. And these are going to be choropleth, isometric, graduated circle, and dot map. And we're going to look at each of these briefly in the coming. So here is an example of a choropleth map, which is a map that uses colors to show variations in quantity or density, percentage, etc., with some kind of defined geographic area. This, for example, is one for the United States, and it's not necessarily by counties. Some look like by counties, but if you look at Idaho, that's certainly not counties in Idaho. And each color is going to usually depict some range of values. So if we look at this map, and if we kind of look at California, we can see a value of a dark orange color there, -4 or less, which is extreme drought. And that's kind of on the eastern side of Idaho, of California, along where Nevada is. And then you can kind of look at other places where it's dark green, which is +4, which is above, which is extremely moist, meaning it gets a lot of some kind of precipitation. So this is a choropleth map. Another kind of choropleth map you might have seen, especially time around presidential elections. You'll see a red or a blue map depicting which way it kind of went for which president, Republican or Democrat. The next is a isometric map. And an isometric map uses these iso lines. And iso means the same, and lines means lines, so the same line. And these are lines that connect equal values to illustrate continuous data such as elevation, air pressure, and precipitation. And you'll be using all of these types of things, elevation, air pressure, and precipitation in your labs. So in your text on page 35 through 36, it briefly identifies 5 different types of isolines that you should be familiar with. And here on this slide, the right-hand image here is a contour line, which you're probably mostly familiar with, kind of showing elevation. So where the contour lines get very, very close together means it's very steep, and where it's kind of far apart means the slope is much more shallow. And the other one on the left is showing pressure. So going from high pressure to low pressure, each one of those isobars represents some pressure. The next here is a graduated circle map. And graduated circle maps use circles that are scaled in proportion to the magnitude of data occurring at some point location. And here we have, in this map, is a graduated circle map showing aggregated assaults by census block group. So each one of these little areas, these boundaries is a census block group, and it's showing you the magnitude of aggravated assaults. Can't really make out the legend, but we can just say the biggest circle is, let's say, 500. The next one is maybe 100, and the next one is maybe 30 or so. Doesn't really matter for this example, but then you can quickly see which census block groups have the most aggravated assaults. Here's a dot map, and it uses these small symbols of uniform size, not scaled like we just saw in the previous slide, but they're typically solid circles, and are used to emphasize spatial patterns of some kind of phenomena. And here it shows the number of cattle and calves sold in 2007, and one dot represents 10,000 cattle and calves. So what's nice about these maps is you can kind of quickly see where the cattle are, kind of through Texas and up through the Midwest there. And you can see also in Idaho, kind of the southeastern part of Idaho, central California, and so forth of where these cattle are. These are dot maps. And each dot doesn't say exactly where the cattle is in terms of that county. It's just somewhere in that county. Furthermore, when discussing maps, map scale is important. And the map scale is the ratio between the length measured on a map and the corresponding distance or length on the ground. And map scale allows you to measure distances, area, or compare sizes. And so there's 3 different types of map scale that we want to talk about here. The first is a verbal scale, and this states in words the ratio of the map length, the map scale length to the distance on the Earth's surface. So for example, 1 inch to 1 mile, which means that 1 inch on the map is equal to 1 mile on the ground. And I'm sure you've seen this, and this is relatively common. The next is a representative fraction. It's a scale is a ratio or a fraction that expresses a mathematical relationship between the map and the ground. For example, a 1 to 24,000 representative fraction means that one map unit is equivalent to 24,000 ground units. And because a representative fraction carries no units, for example, doesn't carry inches, centimeters, kilometers, miles, or anything like that, it means that the representative fraction scale can be compared between different maps. And converting a representative fraction to a verbal scale is very easy. Simply select one unit and apply it to both, and that's kind of key. The 1 and the 24,000 in this example has to be the same exact unit. It has to be miles to miles, inches to inches, kilometers to kilometers. So in the above example, we can write a verbal scale as 1 inch equals 24,000 inches, or 1 meter is equal to 24,000 meters, and so forth. But as I said, you cannot mix units. You can't say 1 mile is equal to 24,000 kilometers, or 1 kilometer is equal to 24,000 miles. It has to be the same exact unit. And finally, representing a representative fraction always begins with a 1. It can't be 2 to 24,000 or 3 to 24,000. It's always 1. And the final is the graphic scale, and it uses a line marked off in graduated distance, such as feet, meters, miles, kilometers, as in this example. And of these 3 different types of scales, this is the only one that remains correct when a map is going to be reproduced at a larger or a smaller scale map. So if I take a map that has a verbal scale or a representative fraction on it, and I put it on the Xerox machine and I shrink it, those units, that measurement is no longer accurate. But if it has a graphic scale, and I make that enlarged or reduced, the scale bar, the graphic scale, moves with it, and therefore will remain accurate. So make sure you understand that. So here we're talking about large and small scale maps. And a large scale map is one that is relatively large representative fraction, which means that the denominator is small. So for example, a 1 to 10,000 is a larger value than, for example, 1 to 1 million. So a 1 to 10,000 would be considered a large scale map in comparison to a 1 to 1 million size map. A small scale map has a small representative fraction, which means that the denominator is very large. So another way to think about this is a large scale map shows greater detail than the scale of a large scale map than a small scale map. And this is illustrated in this series of maps here. Note that a 1 to 1,300,000 is a larger representative fraction compared to the 1 to 95 million, which it shows much more detail. So you can see the small scale map shows all of the United States, and it has no detail. You're not seeing roads, you're not seeing rivers, and so forth. And then as we get to a larger and larger and larger scale map, you're seeing more and more and more detail. So it's kind of the reverse of what you would kind of intuitively think. But I always think of large scale, large buildings meaning more detail. So and when you're having a large scale map, since you're showing more detail, you're going to be only able to show a smaller and smaller and smaller area. So in a small scale map, you saw the whole United States. Then we're moving down into the next map, a smaller area around Atlanta. And then now in this large scale map, you're only showing just part of downtown Atlanta in Georgia there. So a map projection, so somehow when we make a map, we need to take the real world and we need to project it onto a map. So basically we're taking something that's 3D and we've got to make it 2D. And so a map projection is a way of representing or portraying all or part of the curved surface of the Earth onto some flat surface, piece of paper. So a spheroid can't be flattened into a plane any more easily than, like, an example of a piece of orange peel can be flattened. Imagine if you had a piece of an orange peel and you're pushing it down on the table. It's going to rip, it's going to stretch, it's going to stretch out far, it's going to be compressed. So representing the Earth's surface in two-dimensional causes some kind of distortion in the shape, area, distance, or direction of that data. However, the cartographer can choose to control or reduce one or more of these distortions, although not all distortion can be controlled for it in one map. So there are two kinds of map projection properties, equivalence and conformality. Equivalence is going to preserve the area of the features, while conformal preserves the shape. So no map can be both equivalent and conformal. So it's going to be the map maker's task to decide which is more important. So for example, in equivalence, where we're going to be preserving the area, so maybe if you wanted to compare areas, if you wanted to compare the acres of cotton being produced for different counties, well, preserving the area, if you're going to be doing some kind of area calculation, that would be important to preserve. But maybe if you're navigating the coastal waters off of California, well, maybe a map that preserves shape is going to be more important, so you know where the land kind of jets out, where preserving area is not of importance. So types of map projections. So the most projections are derived from some mathematical formulas, and don't worry, you're not going to have to do any of these kind of calculations or anything like that. But some are easier to visualize as projected onto some kind of developable surface, and we'll explain that here in a little bit. Therefore, projections are commonly classified according to the geometric surface from which they are derived, and we're going to look at conical, cylindrical, and planar. They're also called azimuthal. And many of these projections, they can't be easily related to these three surfaces as described. They're kind of called pseudo or modified or individual or unique kinds of projections. So the first is cylindrical. And to imagine this, just imagine you have the Earth, and you're going to wrap a piece of paper around the Earth to form this cylinder that touches the equator all the way around the Earth. And shine a light from the center of the Earth, and it's going to trace this image that is projected onto the paper, and then the paper is taken off the cylinder, unfolded, and then this is the image that you have down at the very bottom of this slide. One thing that's important when we kind of talk about this, wherever this piece of paper that we're wrapping around the Earth, wherever that touches the equator, or the Earth, in this case it's the equator, there is no distortion there. The map is perfectly accurate at that point. But as you move north and south, distortion is going to increase. And in this case, the closer you get to the poles, the distortion is going to be the greatest. The next is the planar or azimuthal, and a piece of paper is on a single point on the Earth, and then a light shines through the center of the Earth, and this part of the image of the Earth is projected up onto this piece of paper, and we can see that here on the bottom. Again, wherever that piece of paper touches the Earth, and in this case it's going to be touching at the North Pole, there's no distortion, but as you move outward, distortion gets greater. And next is conic, and conic projections are nice for showing kind of east-west projections. So for example, the United States is a conic projection a lot of the time. And here we wrap a piece of paper around the globe that forms a cone. Once again, you shine the light through the center, piece of paper. The image of the Earth is kind of projected onto this piece of paper. And once again, where this piece of paper touches the Earth, there's no distortion again. And so this is kind of a way to visualize how this is done. Obviously, as I said before, this is done through mathematical equations, not just by shining a light onto some paper that's going to pick up the Earth. So this is just kind of a way to think. Another important tool to the physical geographer is something called the global positioning system. And the GPS is a satellite-based navigation system made up of a network of 24 satellites placed into orbit by the U.S. Department of Defense. And GPS was originally intended for military applications, but in the 1980s, the government made the system available for civilian use. And GPS works in any weather condition, anywhere in the world, 24 hours a day. And there are no subscription fees or setup charges to use GPS, although you do have to have some kind of GPS receiver to use GPS. So how does it work? Well, first, GPS satellites circle the Earth twice a day in this very precise orbit and transmit a signal information to the Earth. The GPS receivers take this information and use something called triangulation to calculate the user's exact location. So essentially, the GPS receiver compares the time a signal was transmitted by a satellite with the time it was received. And the time difference tells the GPS receiver how far away the satellite is. Now, with distance measurements from a few more satellites, the receiver can determine the user's position and display it on the unit's electronic map. So a GPS receiver must be locked onto the signal of at least 3 satellites to calculate a 2D position, that is latitude and longitude. and track movement. With 4 or more satellites in view, the receiver can transmit or can determine the user's 3D position, that is the latitude, longitude, and altitude. And once the user's position has been determined, the GPS unit can calculate other information such as speed, bearing, and track trip distance and distance to destination. And GPS is being employed in a variety of different ways, such as ground, air, and sea navigation. It's used to produce highly accurate maps and record land deformations caused by earthquakes and volcanic eruptions. And GPS has shown up in a number of commercial products to the public, from standalone units in cars for navigation, cell phones, digital cameras. And there's also a popular use of GPS units is in this high-tech treasure hunting game called geocaching, where you use GPS units to find hidden objects. The last tool that your book discusses is something called Geographic Information Systems, or simply just GIS. And GIS, if you're interested in GIS, I teach a GIS class called Fundamentals of GIS. It's called Geology 126. So if this sounds of any interest to you, or you plan on kind of going on in any kind of natural resources, I encourage you to take that class because it'll be quite valuable to you. So what is GIS? Well, GIS is a computer-based information system for the capture, storage, retrieval, analysis, and display of spatial data. And spatial data, as you'll recall, is any kind of feature that has some exact location that can be defined. For example, your house has some kind of geographic location. It has a latitude and longitude, and it can be mapped. Trees, rivers, roads, temperature, and so forth all have some kind of spatial data because they have some kind of latitude and longitude that can be associated with them, and so you know exactly where they are on the surface of the Earth. So there's a simple way of visualizing geographic information systems, and sometimes GIS is a little bit complicated of a thing for students to visualize without really kind of delving into it and really seeing it. But one way to think about this is a set of overhead transparencies. Now, on each transparency is a map of some kind of particular data set. And in this example here, I have the bottom transparency is the coordinate system. It's just the latitude and longitude upon which all the other layers will be aligned to or registered to. So the second layer in the map is industrial sites. So industrial sites, you're going to want to, the reason why you have latitude and longitude is you want to register where these industrial sites are in the real world. So when you're building your map, they have to be the exact latitude and longitude so they make sense. Then the second layer is shopping centers, the fourth is bus routes, and kind of so on. And by layering this information one on top of the other, a geographer can show relationships and degrees of connectivity between various land uses and transportation routes. So for example, a transportation geographer might want to plan some new bus routes between an area where there's a large amount of increase in population density to maybe a new business location. So where are we going to make this new transportation route? You know, what kind of buildings are we going to be going through? What kind of land uses are going to be there? So we kind of can do some kind of quick analysis using GIS. And geographic information system is being employed in a number of geographic issues. For example, flood hazard mapping, earthquake hazard studies, economic market area analysis. And that's always kind of an interesting one since I kind of enjoy doing GIS for market area analysis and demographics. For example, let's say you wanted to open up a new Petco store. Well, you're going to have some kind of different layer, different transparency in terms of, well, are there any other Petcos nearby? Are there any other PetSmarts nearby? Who are your competitors? And you want to know where they're located at. You also want to be probably located near other stores in a mall, so you kind of attract those people. You don't want to be out in the middle of nowhere because then you won't have any kind of customers. So you kind of have all these different variables that you want to compare, and with GIS you can kind of put those all together, compare them together to come up with the ideal results of where, for example, my Petco store should be. So here how GIS can be used, mapping where things are. And this is a map of the location of earthquakes, shaking hazards, which are essential to creating updated building codes used in the United States. So as you can kind of see, lots and lots of earthquakes in California because of the San Andreas fault line there. So as you can imagine, if you're in California, you want all your buildings up to code for earthquakes, where in other parts of the country, not so important, not so many earthquakes. Here's a GIS map that's created by Core GIS, which is a small private GIS company, and that illustrates agricultural land and population densities within a 50 and 100-mile buffer around the Seattle area. And the idea here is for sustainable agriculture, showing where people live and where agriculture lands are, and whether or not you can get food from these farms to local people. So you can check out this website down below on this map, and it gives you a lot more information about this. But I thought it was just a great map that kind of illustrates, in a simple way, how GIS can be used. And here is another great way of GIS being used. In the left-hand map, you have this 1951 land cover, and we can kind of see in 1951, overwhelming dark green there, and that was forest. And then we can jump to 1999, and we can see the change. And we can see that the forest has greatly decreased, and now the prominent color here is yellow, which is residential housing. So you can see that forests are being cut down for residential housing. And so this is kind of a great way to kind of use GIS to make some kind of analysis. And if you could also figure out, well, what's the acreage of forest being lost? You can calculate these types of things. So this map kind of conveys this data quickly and easily. And that's kind of one of the powers of GIS. Here is a great video that discusses maps, GPS, GIS, and a lot more. This is from Penn State University, something they call their geospatial revolution. If you click on the link, it'll take you to their first episode, but there's several other episodes on there that I encourage you to listen to and watch. It's not required, but if you're interested in kind of geospatial technologies or GIS, these kind of things interest you, I think you'll find it pretty interesting. It's pretty cool. The remaining slides are these concept quiz checks that I'll let you kind of go through at your own pace. Once again, if you get onto the slide, right-click, and you can pause it, and then once you've come up with your answer, you can right-click again and say resume, and you can kind of go through these slides and check your knowledge of the material. If you understand these quizzes, these that are coming up here, if you understand these questions, you should do well on the quiz. The quiz won't have these exact same questions, but there'll be ones that are very similar. So if you feel comfortable with these, then you should be fine on the quiz. And that concludes Chapter 2, Portraying